Right, we are discussing chemical bonding. Before I get into details, right, let me explain what exactly is a bond. Last time I did do that. Let me explain properly. Remember that a bond is necessary for two atoms in chemistry to achieve stability. And remember, stability is always measured in terms of energy. And stability is a function of energy, and stability and energy are inversely related. So whatever is done by atoms, there is only one purpose in chemistry. That is to achieve stability, and stability should be always viewed in terms of energy. And stability and energy are inversely related. Lesser the energy, more is what? Stability. So understand that when the atoms are approaching each other for bond formation, whatever explanation might be given, like they have not achieved octet, they're trying to achieve octet or something like that, but ultimately in energy terms, the energy of the system decreases. That's why thereby they are attaining stability. So someone is asking you that why atoms combine to form molecules, then you understand that a molecular system is more stable than the atomic system. So the two atomic systems combine to give you molecule, and in the process the energy is released and thereby the stability is achieved. That is the best answer you must be giving when you're getting into higher classes. Right? Your teachers told it right, that you don't have an octet, so let's come together, or you donate the electron paid to me, I achieve octet, we both share. These are all the other stories of bond formation you must understand. But otherwise, whatever is happening in chemistry, you must be explaining in thermodynamic terms, that is energy terms, and that's nothing but what? Energy lost. Greater is the energy lost, greater is the stability that is achieved. You must understand that, right? And in the process, before we actually get into the spectrum of subtopics which are extremely important for JEE Advanced or JEE Mains or any end of the pre-engineering test what you wanted to write, let me give details first, then I think we'll link it to the application part where you'll be writing your exam, right? And first of all, fundamentally, let me spend some time on what exactly is a bond. Well, a bond is nothing but a force. It's not a story. It's not a story. You tell me that you give me one electron, I give you one electron, we both put it together at the center, we both share. This is one of the ways to explain what bond, and we are not interested in that. Remember that a bond is a force. A bond is basically a force. It is a force. I would like to underline this word and remark, the bond is a force. The force that binds two atoms or ions in a molecule. So the force that binds two atoms in a molecule can be called as what? A bond. You must understand. So bond is basically a force. If you understand that the bond is a force, then force in chemistry, force in sciences are no single force. You have several types of forces that exist. And it's a common sense that between oppositely charged ions, right, you have your ionic force, the strongest of all, right? And if you don't participate in bonding and you don't have ions, then I will induce a force into you. Then you have that van der Waals force. That's nothing but another type of bonding. You must understand that, right? And I have another force, that is covalent force. This is for people who wanted to participate in what? Covalent bonding. And the other one is, of course, what? Metallic bonding, which exists between metal atoms, which are supposed to touch each other in a metallic solids. So when you can actually extrapolate the topic of chemical bonding only when you understand that a bond is a force. Yes, for your understanding, for your solace, you can tell me that yes, a bond is an arrangement where people have not achieved octet, they have not achieved stability. Let's place the electrons at the center, both share. These are okay, the perception to understand a bond, but remember that in thermodynamic terms or energy terms, you must understand that stability and energy are inversely related. So atomic systems are unstable, they form a molecular system, and in the formation of the molecular system, I think there the energy is lost and thereby the system is achieving what? Stability. That is our understanding is. If this is the case, if the force is several types, ionic, covalent, van der Waals, an induced force, and then you have your metallic force, then I think even the bonds are several types. You must understand. And let us discuss today electrovalent bond. I think I started it, but let me put it properly so that you can understand better, right? So you understand electrovalent bond, but otherwise I call this to be an ionic bond. This is ionic bond. And remember, ionic bond is basically the essential thing is this. Remember this. This is basically a bond between a metal and a non-metal. You must understand. So basically, if you are given 4 choices and you're asked to choose between, which combinations will give you a metallic bond or a covalent bond, then students must understand that if you choose a metal and a non-metal, it's essentially ionic. If you choose a bond between 2 non-metals, it's essentially covalent. You must understand. But I think when you say this, when you say the essential condition is basically a bond between a metal and a non-metal, then several questions arise before me. What are those? If you look into the periodic table, when you go to the extreme left, you have 100% metals. And metallic nature or metallic character is basically a function of what? Size. And the biggest sizes in chemistry are possessed by people who are placed to the extreme left, right? And the non-metals are placed to the extreme right. And more specifically, we say a metal, the best metal is placed to the extreme left bottom, and the best non-metal is placed to the extreme right top. If there are so many, if the metallic character is varying in every position in the periodic table, and the major variance in a period is from left to right, I think the metallic character decreases. So for our own discussion, if you simply say that a bond is between a metal and a non-metal, then if I can continue this, then I can write a good metal versus a very good non-metal. Then I call this to be 100% ionic. And I call this to be 100% ionic. That means that you must be a good metal, you must be a good non-metal. But not every metal is good. It's simply a metal, right? So I can simply say this is the first group, and this might be the 7th group, that is the halogens, and a bond between these two seem to be 100% ionic. You must understand. That seem to be a 100% ionic bond, that clearly indicating that a bond between a 2nd group element and the 7th group element is not that much ionic when compared to the 1st and the 7th. You must understand. And when you move away from the 1st group, go to the 3rd group, and then the 7th group, then the ionic character goes on decreasing. And if you actually look into the transition metals, and if you take silver, right, and go for your 6th group or the 7th group elements, then I think the percentage of ionic character further drops. So this actually creates a big discussion, right? A big discussion between an essential condition and a sufficient condition. You must understand that if you just wanted to pick a metal and a non-metal, then it's essentially ionic, right? Is that sufficient for you? No, absolutely not. If you are a good metal and a good non-metal, then you are 100% ionic. When you move away from the 1st group, then the metallic character basically decreases, and then even the percentage of ionic character also decreases. And then when you say percentage of ionic character decreases, then it also means that the percentage of covalent character is also increasing, right? But remember, I just wanted to insist twice or thrice for you without any confusion, right? Remember that a bond will remain ionic. A bond will remain ionic, right, when it is between a metal and a non-metal. Forget about how much percentage of ionic character is there and how much percentage of covalent character is there. But remember that a bond between a metal and a non-metal is basically essentially ionic, right? And I insist on this because what happens is if you take sodium, then it is 11. So this is the outermost electron in it. and then you have chlorine. Then you understand here, this is the 6 electrons it has, 7 electrons it has, right? 7 electrons it has, because chlorine belongs to the 7th group. Then what you're doing here is basically you give off this to it. And the consequence is it develops a positive charge and this develops a negative charge. So the essential condition is basically you should form a cation and an anion. That means that the electron is leaving the shell. The electron in sodium is basically leaving the shell, completely left the shell, and the shell got vanished. It left the shell. When it left the shell, then understand that this ion, this is a complete positive charge. This is a complete positive charge. Remember that. Unit positive charge complete. Unit positive charge complete. You must understand that. Complete. Because the electron has left the shell. It's no question of sharing. And regarding chlorine, it has taken away the electron. It has taken away the electron. And in the process of sodium losing and chlorine taking, both have achieved octet. This has got now 10 electrons. That has got 18 electrons. This is neon and that is argon. They have attained the noble gas configuration and both are what stable. This is a high school concept your teachers might have told you. I'm just briefing you. But one thing I wanted to tell you is a bond between a metal and a non-metal is essentially will remain what? Ionic. Now whether it is 100% ionic or not is not the issue, but remember that a metal and a non-metal is essentially what? Ionic. But at the same time, good metals are there, bad metals are there. So if it is a good metal and a good non-metal, it is 100% ionic. If it is not, then some percentage of what? Ionic character, percentage of what? Ionic character decreases and the covalent character will be more in such compounds. But what I wanted to insist is whether you have less ionic character or more covalent character, but the compound remains to be an ionic compound because the electrons have actually left the shell. They have left the shell and the ions are formed. And when the ions are formed, there exists an electrostatic force of attraction between them. And then I consider that to be what? An ionic bond. So finally, what I wanted to tell you finally is, right, a bond between a metal, non-metal is ionic. But if it is between a good metal and a good non-metal, it's 100% ionic. When you move away from left to right, the metallic character decreases. So even the ionic character basically what? Decreases. But that doesn't mean that it's not an ionic compound. Yes, it is, and it will remain. Because the electrons are left the shells, right? And if I can illustrate more clearly without any confusion to you, then observe here. So what I said, a good non-metal and a good metal is essentially ionic. That means that this is first group versus 7th group. Then what you do, a bond between a transition metal, that is a D block, you can take zinc, you can take lead, you can take silver. You must understand when the transition metals, and this is versus the 6th or the 7th, they are also ionic, no doubt about it. They are also ionic, no dispute in that, right? But at the same time, they are not 100% ionic. They are less than 100% ionic. Some will say 80%, 90%, the remaining 10%, they are actually possessing some covalent characteristics. I'm not telling they are covalent bonds. They possess somewhat covalent characteristics, right? They exhibit some covalent compound characteristics remaining to be what? Ionic compounds. That's my contention, right? Now understand when we basically say they possess some covalent characteristics, then people wanted to ask me, how do we measure that? How do we know? Because every stride I take in the periodic table from left to right, the metallic character is decreasing. Every position I take in a group from top to bottom, right? You have variance in the metallic character because from top to bottom, the metallic character is basically increasing. And from left to right, the metallic character is what? Decreasing. So every position, one step, what you move from top to bottom or left to right, the metallic character is decreasing. So it's a huge thing what we are actually discussing, and people wanted to know that how does this variance, and is there any way to monitor or supervise this variance, and are there any rules? Are there any rules? And my answer to this question on behalf of you is, of course, we have what? Rules, no doubt about it. We do have rules, right? If that is the case, then watch here. Watch here. Let us start off with basically, right, observe. Here is a question. Well, you reason with me. I think you'll agree. Let's compare the two ionic compounds. Let's compare the two ionic compounds which I'm writing for you, right? And that is your NaCl versus the AgCl. NaCl versus what? The AgCl, you must understand. And in NaCl versus AgCl, sodium is a metal, silver is a metal. So I call this to be, this is the first group, and this is the D block. That's a D block element, silver. Sodium is first group, and this is a bond between a metal and a non-metal, metal and a non-metal. But remember, there's a metal and a non-metal, metal and a non-metal. Both are ionic. Both are ionic. But if they both are ionic, they must be exhibiting ionic properties. And one of the most visible and convincing properties of ionic compounds is basically you teachers were telling you in school that ionic compounds must be soluble in water. Look at what I'm telling. What I'm telling is both are ionic. So they must be exhibiting ionic properties, and one of the properties is basically they are soluble in water. What we will do, we'll put them in water. If we put them in water, then this one in water, right? And this is extremely soluble. This is extremely basically what? Soluble. And this fellow, AgCl, this compound AgCl, is basically, forget about solubility, this is basically a precipitate. This is basically a precipitate, you must understand. So both are ionic compounds, but one is extremely soluble in water, the other is insoluble in water, and it's a precipitate. Well, that means that I have a feeling, even though, I call this like this, even though both are ionic compounds, but still, this guy, AgCl, is showing some covalent properties. It is covalent substances which are basically not soluble in water. Our teachers told us. So it is covalent compounds that don't dissolve in water. So I get a feeling, even though both are ionic, but still some percentage of covalent character is crept into ionic bonds. So covalent character in ionic compounds is very common thing what we see. You must understand that. There, if I can give you some volley of questions to you, look into this. You know, you need to reason all this. We must be reasoning all this. We must be reasoning all these. One, I can simply say NaCl soluble in water, AgCl is a precipitate. AgCl and Ag2S, in fact, both are what? Precipitates. Right? Being ionic compounds, being branded as ionic compounds, but still, one is a precipitate, the other is what? Soluble in water. That's number one. We need to reason this. We need to reason all this. And the reasoning things are basically questions in exam. These are the questions in exam. And the second reasoning is basically this. Look into this. The second one. This is important. That is, the main ore. Now what is an ore? An ore is nothing but a mineral from which the metal is extracted cheaply, right? Without any cost, with less cost. So everywhere you find zinc, but not every zinc you get it it can be considered as an ore. There are some main ores and some are not main. So ore is basically a part of the mineral where the metal is extracted cheaply with less cost. So what I'm basically telling you is the main ore of lead is galena. That's PbS. The main ore of lead is galena. And let me tell you, the mainness, what we are speaking, the main. There are two things attached to this. The financial element, that is you're extracting the metal, you're basically extracting the metal. Lesser cost, that is one of the criteria for being an ore. The second thing is, it is actually linked with this. It's a question of abundance. If you are rare, your cost anyway increases. And I can tell you that if you dig the entire surface of the earth, the galena is found more. That I'm speaking of abundance. If you wanted to compare galena versus litharge, that is PbS versus PbO. PbS versus PbO. And more abundant is what? PbS. And let me tell you, not litharge. That's PbO. And remember, to answer this, it's not philosophical or religious. It's natural thing. Understand that if you dig the entire surface of the earth, searching for ores of lead, the more abundant is galena and not PbO. So what I'm trying to reason with you is basically the Pb plus 2, if given a chance of combining with these two in nature, if given a chance for lead plus 2 ion to combine with O minus 2 or S minus 2, in nature, it has basically combined more like this. This is more. And this combination, PbO, is basically lesser. You cannot turn religious. You cannot turn philosophical and tell people, yeah, it happens because God has created this. It's not like that. It might be a God creation, but you need to reason at least why in a convincing way. Why is the issue? Similarly, you have 3 MgS is basically less soluble in water compared to MgO versus the MgO. So I can go in for some volley of questions. I restrict myself through 3 reasoning things for you. Why? Look at all this. Whether it's a reasoning 1 or reasoning 2 or reasoning 3, we are basically dealing with a metal and a non-metal. This is basically a metal and a non-metal, metal, non-metal, metal, non-metal, metal, non-metal. Everywhere it's a metal and a non-metal. So it must be what? Ionic. If it is ionic, they must be what? Showing ionic characteristics. It's not the case. It is not the case. You can actually see some of them are actually showing some percentage of covalent character in spite of being what? Ionic character, ionic compounds. And I read it for you. See this. This NaCl extremely soluble in water. Ag2S and AgCl are basically precipitates, indicating some percentage of covalent character has crept into these compounds. And look at this. The main ore of lead is actually galena and not what? Litharge. Similarly, the main ore of silver is silver glance. That is Ag2S and not Ag2O. You must understand, right? So the reasonings are there before you, and we must be convincingly explain why such a thing should happen. How do you explain this? Turning philosophical, turning religious would be easy for you. This is God's creation. What shall we do? But as a science student, we must be presenting some convincing explanation, sticking toward chemistry. And I'll be doing that. Watch. To explain all this, I propose to you, watch. To explain all this, I propose to you the concept of polarization. The concept of what? Polarization to you. Now, if someone is asking you, why are you proposing this in the first place? Why? Let's write the aim first. Let us write the aim first. The aim of this is, why are we doing this? The aim. This is basically to judge. To judge. Covalent character in ionic compounds. So no confusion, please. We are dealing with ionic bond. We are basically dealing with what? Ionic bond. And we are trying to explain why some properties, in spite of being ionic, why some compounds, in spite of being ionic, are basically showing deviation from the properties of ionic compounds. And we need an explanation. We are with ionic bond only. When you are with ionic bond, why I need to remind you every time is basically understand that when you are with ionic bond, you have an electrostatic force between the ions, and the particles that are present, the primary particles that are present in ionic compounds are ions. When they are ions, remember there is transfer, complete transfer of electron from a metal atom to a non-metal atom. Complete transfer. It's no partial transfer. There is complete transfer of electrons, whether it's 1 or 2, from the metal to a non-metal, resulting in a cation and an anion. When the result, then there exists an ionic force of attraction, that is nothing but what? Electrostatic force of attraction. Thereby we call this to be an electrovalent bond. Then if you ask me, what's the issue then? Well, the issue is nothing but you have what? Ionic force. But why are some compounds, in spite of being ionic, are showing covalent characteristics? For that, I'm providing an explanation to you. That's nothing but the concept of what? Polarization. And the concept of polarization is presented to you because we need to judge covalent character in ionic compounds. That's the reason why I propose the concept of what? Polarization to you. Right? Let me explain what is polarization. Let me define first. Well, if I define what is polarization, look at this. Polarization. What is this? What is this? The distortion. So if someone is asking you, what is polarization? I would like to give a pause here. It's nothing but distortion. Distortion in the sense, if I'm still like this, when someone is approaching me, I get distorted. I get distorted, not in this body language, but somehow I get distorted, distracted, you can say. Or our simple language, then we call that to be shyness. You feel shy. And the shyness in English is basically distortion. And why are you shying away? There might be some reason. I think the environment or surrounding you might be changing. Hence you are exhibiting what? Shyness towards towards anything approaching you. So it's distortion. The distortion. So polarization is basically distortion. I would like to underline. It's nothing but what? Distortion. Now the question arises, who is getting distorted? Who is getting distorted? So distortion of negative charged cloud. This terminology is what I'm using is a matured one. You must divorce all the perceptions you have made in your earlier classes. Your teacher might have called this to be an anion very simply, because you say negative charge cloud, and if I can write it for you, I call this to be an anion, let it be B minus. I think you understand better when I call this to be an anion. Your teacher told like that to develop a perception. But remember, you must change your thinking. That's the distortion of negative charge cloud. Well, look into this, what I'm writing, negative charge cloud. So I view, and you should be viewing after this class. You must be viewing, you must be dreaming after my lecturing that a negative charge cloud, that is an electron-rich substance which develops a negative charge on your head, is like a cloud. Remember that. And when I use the word cloud, two things come into my mind. One, it has an irregular boundary. And remember, it has an irregular boundary on the top. It has a diffusing property. It's just relaxing. A cloud, the way it relaxes. Similarly, an electron relaxes. Or a negative charge cloud or the anion relaxes. So what I'm telling is basically the distortion of a negative charge cloud. In your terms, but for better understanding terms, I call this to be an anion. So the distortion of negative charge cloud, why are you getting distorted? Because the environment surrounding you have suddenly changed. Someone is coming towards you, you're getting distracted, you're getting distorted, you feel shy. No, it's a common sense. The negative charge cloud or the anion is getting distorted. It's getting distorted on approach of someone. Who can be the someone? Well, the negative charge ions are always approached by positive ions. It's a common sense. No other fellow will approach it, at least voluntarily. So you have an anion, it's getting distorted, distracted, feeling shy, and there is only one reason. People approach a negative ion, and those people are nothing but a fellow who is having a positive charge. That's a cation. So I continue writing, what is polarization? The distortion of negative charge cloud on approach. On approach of a cation. That is A plus. So when a positive charge is approaching a negative charge cloud, it's getting distracted, distorted, feeling shy. Now, people should understand. You must have common sense. Extrapolate your common sense. So when a positive charge is approaching and the negative charge is getting distorted. So when it's approaching, fine, I'm getting shy. And when you're coming close towards me, I'm feeling more shy. But even though I'm feeling more shy, it's basically the negative charge when it feels shy, it's actually inviting the positive ion to please come more forward. And what is the reason for approach? A positive ion is electron deficient. And naturally it will approach the negative ion to share some of its negative charge. And even the anion is ready. Even though it's feeling shy, it's asking the cation, please come. Even though I'm feeling shy, please approach me. So in total, there is a conducive environment. There is basically a conducive environment created between a cation and an anion, because cation is approaching, the anion is shying away but inviting the cation. Why? To share its negative charge. And look into this word share. Cation is already pre-existing. Anion is also pre-existing. That means electrons have transferred from a cation toward anion. That means the prerequisites for ionic compounds have already been there. So an ionic bond is established. Remember that. But the cation, when it approaches the anion, right, the negative charge is somewhat shared. So if I can complete it, the distortion of the negative charge cloud, anion, on approach of a cation is called polarization. Is polarization, you must understand. And remember, don't forget the aim, why we are discussing this. We are discussing the concept of polarization, and the aim you must not forget. The aim is basically to judge some covalent character in ionic compounds. So we are still with ionic compounds only. We have just started it. What I'm trying to tell is some ionic compounds possesses some covalent characteristics. To explain that, we must be giving some convincing explanation. Hence, I introduced to you the concept of what? Polarization to you. And to judge the covalent character in ionic compounds, and hence I propose to you what is polarization. It's nothing but the distortion of the negative charge cloud on approach of a cation can be called as what? Polarization. So what I'll do, I'll give you a pictorial representation of it, and then comments are made after that. Look at this. This is an irregular boundary, and this is the B minus, and this I call this to be a negative charge cloud. Negative charge cloud. And now comes a cation. Now cation is at a legitimate distance, no distortion. If the cation is at some larger distance, then I think you don't find any shyness in this, because the cation is far away. But if the cation is approaching it, right, approaching and going close, then the negative charge going close and doing what? Because you are electron deficient, your positive charge indicating that you are electron deficient. And your electron deficiency, your want of electrons, so you approach a negative charge cloud, you have a negative charge here, you approach and start sharing it, right? So then the shyness, I can show you the shyness to you. This is the original structure of the cloud, and the shyness is something which gets distorted. That is the cloud now. It is the same B minus. And now what is happening? This A plus is now too close to it. And what it will do, it will basically start sharing the negative charge. And I would like to underline here the sharing part. When you go close to an anion and start sharing its negative charge, then what happens? Some percentage of covalent character is basically induced. And that's into ionic compounds. You must understand that. That is a pictorial representation what I'm making. Look at this. When the cation is far away, I don't feel any shyness. Absolutely no shyness. I'm not distorted. But when you start approaching it, the cloud gets distorted. And it's not refusing to bond, not refusing to share. It's asking the cation to, come down. There is a conducive environment in this whole process. And when it goes close to it, it gets distorted too much. And it asks the cation, come share my electrons. And this word sharing is what is important, because in ionic compounds, sharing has been introduced. Even then you have a cation and an anion. You must understand that. If there is absolutely no distortion and the cation is actually far away, then it's 100% ionic bond. Ionic bond. But since you are actually approaching it, going close, then the percentage of ionic character basically what increases. You must understand that. So now the obvious thing left in our mind, see, look into this, two things I'm putting it. If the cation is far away and you don't experience any distortion, you're 100% ionic, you're soluble in water. No dispute in it. But if you are actually started sharing, coming close to the anion, sharing, that means that some percentage of covalent character has been induced into ionic compounds. Hence you are insoluble in water. Now we wanted to answer very clearly. We wanted to answer two things. One, who is far away, who is left over, and is not interested to approach. Is not interested to approach the anion. Some people are not. And who are those fellows? Who are those fellows who are getting too close to the anion? Basically, in periodic table, not every cation is of the same character. So some people wanted to get close. Some people don't want to get close. They can't. So they stay away. When you stay away, no distortion. You just stand like this, even though they are approaching you. It's just stand like that. You don't have any what? Distortion, no shyness, no polarization, no question of sharing. When someone is approaching you, you do all this. And I'm not surprised an inch, because cations are formed by so many metals, man, in periodic table. Someone will approach, someone will stay away. What is the big deal? Now the question arises, who will stay away? Who will approach? That's a question in exam. That's about cation. But there are some people, even though some people are approaching, they don't distort at all. You can say in terms of this fellow also, the anion also. Some people are more shy, some people are not. Some people are totally not shy, they just stand like this. Oh, you're approaching me? So what? So what, the big deal? I'm not shying away, I'm not distorting. I'm not distorting at all. You come down. I just stand like this, no distortion, I don't care. Some cations don't care, some anions don't care. Some approach, some don't approach. So where are we standing now? And we want a clarity. And we wanted a clarity. Who will approach, who won't approach? We wanted a clarity. Who are those cations who will approach? Who are the cations who stay away? Who are the anions who are more shy? Who are the anions who are not shying? So what we will do, so I think the comments are imminent. So what we are trying to do is we'll categorize, we will comment, we'll categorize, we will comment on both cations as well as anions, some comments which I'll make. And these comments are become rules. And those rules have been given a name. And let us see that. Watch. These are nothing but the Fargent's rules. These are nothing but the Fargent's rules. Now what this fellow Fargent will do is basically he's commenting both on anions as well as cations. So what is Fargent's rules? These are nothing but the comments made on cations as well as anions, both. He has made comments on both anions as well as cations. Let us separate them. Let us separate them. What are the comments made on cations? What are the comments made on anions? Right? Observe, the first comment what made on cation is, he's asking us, look into this. So many things happen. This is the cation comments. He's commenting on the cations. Now what he's saying, smaller the size of cation. Look at this. Smaller the size of cation. Now immediately student must understand he has done with periodic classification and smaller cations. When you say smaller cations, I think in the periodic table extreme left are the biggest sizes. Extreme left elements possess the biggest sizes because from left to right the size decreases. So left to right basically the size decreases. You must understand that. So when someone is referring to smaller cations, they are to the right. Don't say extreme right. Extreme right are nonmetals. Extreme right are basically nonmetals. So don't say extreme right. So you are moved out from extreme left, which have the biggest what? Atoms. Because sizes of the elements. And then when you're moving from left to the right, somewhere in the middle, that is I'm referring to a D block, somewhere I'm referring to a D block, they seem to be smaller in that respect to period. So left to right, the size decreases. So the smaller cations are not to the left, they are to the right. You must understand in that respect to period rather. So what will happen? What will happen if it is the smaller the cation? He says the smaller the cation in size, then, it says it gets too close to an anion. You must understand. So the criteria for getting too close, you must be small. So when you're small, you're actually too close to the anion. When you do close to the anion, you will have a consequence, right? And the consequence is, distortion more. So you induce distortion more. So when you're getting too close, distortion is more, is shying away, it's inviting the cation because someone has invited, that's why you're too close. You're not invited, you'll be thrown away. So there is a conducive environment in this entire story. So what Fargent is commenting is, he has comments on both anion and cation. And the cation comments have started like this. It says, Smaller the size of the cation, the more smaller you are. You get too close to what? An anion. Too close to the anion. And when you get too close, you will find the distortion or the shyness more. When the distortion is more, it is asking to share the electrons. So when it asks to share the electrons, it says distortion more. Then it says more is polarization. When the distortion is more, technically we call polarization is more. The polarization is more. If polarization is more, then covalent character is more. You must understand. The covalent character will be more. This is the comment which is made by Fajan. And if you have a closer look of this, let's read it again. It's like this. Smaller the size of cation, it gets too close to what? Anion. When you get too close, distortion is more. And what are you doing? Getting close to an anion. What are you doing? What is the purpose? The purpose is to share the negative charge. And you share. When you share, covalent character is more. So simply speaking, smaller the cation, more is simply covalent character. You must understand. Now students must extrapolate and locate the positions of the smaller cations. Where are they in the periodic table? Extreme left, you have the biggest cations, that is alkali metals. Extreme right, you have a non-metals. Don't go to that far away. Stay somewhere in the middle. Left to right size decreases in a period. So if you wanted to compare a 6th period element with a 6th period extreme light with extreme right, I think if you get into the D block corresponding period element is basically smaller when compared to the left elements of the same period. Such cations, so what I mean simply is basically this. All extreme left fellows form ionic compounds. When you actually deviate from the left to right, the covalent character is increasing because the size is what? Decreasing. When the size is basically decreasing, the covalent character is what? Increasing. So that is the comment on what? Cation. Now let us comment on an anion. Because some people are shy, some people are not, some people stay like this, no shying. Who are those fellows? Let us comment. And these comments are nothing but the Fajan's rules. That's nothing but the Fajan's rules. So shall we comment on an anion? Yes, of course. We will see that. Look into this. Some comments with respective polarization on anions. Some comments on anions. That is the B minus, the negative charge cloud. And what Fajan is telling basically is this. See what he's telling. He says, bigger the size of an anion, bigger the size of an anion. The size of the anion is bigger. That means people should all be in a position to locate bigger anions. First of all, anions are placed to the extreme right. And remember that bigger anions are not placed to the extreme right top, but rather they are placed to the extreme right bottom. For example, 6th group, if you take an anion in the 6th group is basically oxygen family. And oxygen family includes what? Oxygen and sulfur. And oxygen is a non-metal, sulfur is a non-metal, so they both form anions. When they both form anions, the bigger anion is of course sulfide ion. The bigger anion will be sulfide ion. And if you take halogens, fluorine and chlorine, down the group the size increases. So naturally the bigger anion would be Cl minus and not F minus. So we just locate where are the bigger anions. First of all, anions are placed to the extreme right. And how to pick the extreme right, fellows? From top to bottom the size increases. So bigger anions are placed to the extreme right bottom. They are basically placed to the extreme right bottom, right? So look at the comments. He says that the bigger the anion, more it gets distorted. So if the larger is the size of the anion, more it's feeling shy. That means smaller cations won't. Smaller cations won't. That means if you look into oxide, if someone is approaching me, the oxide stands like this. Come on, so what? I'm not feeling shy. So what? You approach me, so what? I'm not feeling any shy, and I'm not going to any share my negative charge towards you. I'm not interested in any covalent characteristics. I'm 100% pure ionic compound. This is the language used by oxide ion. So it says because the size of the anion, more it gets distorted, then more is polarization. And more is polarization, more is covalent character. More is what? Covalent character, you must understand. So, if we can sum up both the comments on the anions and the cations, then it looks like this. According to Fazen now, what he's asking us is, right, look at this. He's asking us that, the cations must be smaller, the anions must be bigger, right? And then such a combination of AB where A is metal and small, B is a non-metal and basically big, and such compound AB shall be of course ionic but has covalent characteristics. You must understand. They have what? Covalent characteristics.